Hello, everyone, and welcome. I'm Kathleen McLean, the Manager of Public Programs here at the AGO, and thank you all for coming inside on such a nice day to join us this afternoon for Wolfgang Tillmans in conversation with Kyros Kutulakos and Suresh Sivanandam. So, the AGO operates on land that is Mississauga-Anishinaabe territory. Toronto is covered by Treaty 13 between the Mississaugas of the Credit and the British Crown, and everyone living in Canada are treaty people and part of a treaty relationship based on respect, cooperation, partnership, and Indigenous rights. Today's program, as you might know, is held in conjunction with the exhibition Wolfgang Tillmans To Look Without Fear, which is on view on the 5th floor of the AGO through October 1st. I hope you've all had a chance to see it. So I'm going to briefly introduce our three speakers today, and then they're going to come and talk for about an hour and a half. We'll see how it goes. And we're really thrilled, A, that they said yes to this invitation, B, or maybe A, point two, that Wolfgang is able to come back to Toronto to join us here for a program. He gave a talk some of you might have caught before his exhibition opened, and we're really delighted that he can join us again. So, brief bios. Kyros Kutulakos is a professor of computer science at the University of Toronto. Over the past 2 decades, he's played a leading role in the development of computational imaging, a field that combines optics, light sources, image sensors, and computer algorithms to make our cameras smarter and to give them abilities well beyond those of human vision. Suresh Sivanandam is the interim director of the Dunlap Institute for Astronomy and Astrophysics and an associate professor at the University of Toronto. Suresh has been at the forefront of efforts to enhance the imaging capabilities of large telescopes by pushing the boundaries of optical instrumentation with a focus on advancements in adaptive optics. He uses these developments to study the distant universe and understand how galaxies formed and evolved over time. I feel like Wolfgang needs no introduction, but it'd also be really rude to not introduce Wolfgang. So briefly, Wolfgang Tillmans has, throughout his career, explored and integrated photography's many genres, techniques, and presentation strategies. In 2000, he was the first photographer and first non-British artist to receive the Turner Prize. And in recent years, he's been more directly involved in political activism, in tandem with his ongoing Truth Study Center project that he began in 2005, he's created posters for the anti-Brexit campaign in Britain and in response to right-wing populism in Germany. So I'm really thrilled that the three of them are going to be able to be in conversation today, and I think we'll all end up with a kind of deeper sense of appreciation both for the work of Kyros and Suresh, but also Wolfgang's photography. So in short, we're in for a treat. Please join me in welcoming them all to the stage.
Thank you, Kathleen, for introducing us, and thank you for coming out on this sunny day. And yeah, fantastic that Kyros and Suresh agreed to be here, because I love nothing more than ask scientists questions that somehow have arisen in my ongoing exploration of the world, the visual world, and in particular physics, because even though after puberty set in, my grades in physics and maths nosedived. My first passion in life was astronomy, and I spent from 10 to 13 every day and night that it was clear skies with my telescope at daytime, counting the sunspots and drawing them. And I guess I learned about the importance of careful observation. And when you start sort of even the simplest book, reading the simplest book about astronomical observation, for example, you come across the note that if you want to look at a really faint object, look a little bit to the side of it.
That's right, with your, if you're looking at it with your eye, because this very center of your eye where the optic nerve is, you don't have much ability to see things. So you want to look a little bit off so you can see very faint objects.
Yes, so the central seeing cells are color sensitive, whereas the ones on the outside are only black and white sensitive, but are having a higher sensitivity to light.
Right. The outside of the very core of your field of view, you have rods which are not sensitive to color. They're just sensitive to light, so they're much better at detecting very faint light, faint objects. And in fact, they take some time to get used to darkness. So if you're in a very bright location, you usually have to, and you go out and you see the night sky, you have to wait a little bit before they they reach maximum sensitivity.
So that's not just the opening of the diaphragm.
That happens pretty quickly, but if you go out to see the dark night sky, you have to spend 10, 15 minutes before your night vision really kicks in.
Okay. Yes, so this observing how we observe is fascinating, and I kept this love for astronomy throughout my life, and it kicked back in, I guess, fully in ~99 when the first total solar eclipse in Germany and Western Europe happened, and in a year before, I went to see the total solar eclipse in the Caribbean, and so I've become an eclipse chaser as an adult.
It's still on my bucket list. I haven't seen one yet.
Really?
Nope. No, I've seen a partial, but not a total. I'm waiting for next year when there's going to be one near Toronto.
Exactly. So everybody here in the room, please take note. In April next year, there will be a total solar eclipse that goes all across the US. Does it hit Canada as well?
Yes, it's not. Toronto's just gonna miss it. But if you're in Hamilton, you can catch totality.
And there is one really, really, really important thing I can tell everybody, because when people say, when I say that there's a total solar eclipse, have you seen one? And they say, yeah, I've seen an eclipse. And the thing that what happens between 0 and 99% of obscuring the sun, and the last 99%, and until all of the sun is gone, what happens in that last minute is just such an earth-shattering experience, because light, the drop in light, the human, I believe, sort of really recognizes by halves, and this half becomes exponential as it comes to the end of the eclipsing, and so there is a darkness coming over you, which the brain just doesn't understand, because there is no shift in light color. We only normally know the shift in light color associated with dawn or dusk. And anyway, until the very end of this program, I have a video that I filmed in 2015 that shows that arriving of the moon's shadow in real time. But the starting point maybe of this whole exploration was that of this afternoon was that I thought, let's not talk again about my work, because I've done that in April, but I have this particular interest, and recently been making this video which came about the simple question, is it possible to film the twinkling of a star?
I think you did it pretty well there.
Thank you, because I haven't seen it really. No, it's computer. I haven't seen other examples. The thing is, a star, not by definition, but by scientific appearance, is always only a mathematical dot to earthly people.
Yeah, it's really, really far away. That it's infinitesimally small.
So however much you enlarge it, it never becomes a disk.
Well, yes, and with conventional telescopes that you have access to, or amateur astronomers use, you can never do that. But there are some specialized telescopes out there that use an array of telescopes to be able to observe very, very big stars that are nearby.
Really,
they can actually resolve that. Yeah.
But so the explanation why stars twinkle and planets, which are actually a little disk in the sky, they don't twinkle, is that there is kind of proverbially only one ray of light coming from the star that is bounced around in the atmosphere, whereas from the disk of a planet you have, say, 100 rays, and they are all bounced around differently and that way even out. And so a planet appears non-twinkling and calm in the sky.
Yeah, that's one way of looking at it. The reason, no, but okay, it's a good way of looking at it. Right. So I think the interesting point is what's bouncing the light around, and it's really turbulence in our atmosphere, and the turbulence has a certain size. You can think of it as a scale, and the light from the star is on a scale that's much smaller than that, and so it bounces around a lot. But then, a planet, if you're observing a planet, the scale of turbulence is smaller than the size of the planet on the sky, and so that's why you have this averaging effect, and you don't see it twinkle. So I think your interpretation is correct. It's just another way of looking at it.
Mm-hmm. But then, so for filming this twinkling of Sirius, when you have the image focused, because Sirius does not have a dimension, it would really only hit one pixel, but that pixel would be totally overexposed. And so I quickly noticed when I defocused the telescope, the image would become a disk, which you've been seeing play as a video as you were waiting. And the movement you saw is the movement of the Earth's rotation. And then I filmed this disk and enlarged it, and then I made stills of it, which you see one example here. And I thought, well, on the one hand, it's supposed to be out of focus, but how come there are these details in here, like even these little dots? And that made me, yes, but first of all, the colors is one question. Where do the colors come from? And then where does the detail come from? The colors, I assumed that there would be an effect called chromatic aberration inside my telescope, but I then resorted to Instagram to ask and quickly found out, no, there is no chromatic aberration in the type of telescope that you use, which you can see here. This is the 1982 Celestron 8-inch reflector, a Schmidt-Cassegrain model where you can see the, well, maybe you can explain the...
Sure, yeah, I didn't realize this was going to show up in public. I kind of threw it together in the last moment, but anyway, it's probably mostly correct. So this type of telescope uses both mirrors and a piece of glass. And the piece of glass is at the very front of the telescope. It's almost flat. It's got a little bit of a ripple on it, so it doesn't actually bend light much. And then you have two mirrors, one on the far back and one that's in front of that. So the light comes in, goes through the glass, reflects off the rear mirror, which is the 8-inch part, and then it comes back, hits another mirror, and then it comes to a focus right behind the telescope where you put your camera and get the nice video over there. And the reason it doesn't have much chromatic aberration, so that's when different colors of light get bent in different directions, is because it's a mirror reflects light. Doesn't matter what color of light it is, it reflects it the same way. Whereas lenses, they actually are sensitive to different colors of light and how they bend the light.
And air, does the difference in density of air act similarly as a kind of
Exactly.
lens?
Yes, a very,
Because
very weak lens.
The lens is a lens because the light that passes through it is changing its path. It's a different density. And so different
right.
density of air also slightly changes the path of light.
That's right.
And do we know why?
That's a good question. It's a material property of how light actually interacts with it, and different materials have slightly different interaction properties. And in fact, the light actually slows down in a lens material by approximately 50% as it interacts. So and different colors of light interact slightly differently with that material.
It really slows down?
It does.
I mean, like it's the speed of light is 300,000 kilometers per second. So when it hits the lens of my camera, it slows down to 150,000 kilometers per second.
I think probably around 200,000.
Really?
Yes.
And then when it exits the lens, it speeds up
It
again?
speeds up again, yeah.
Okay. And so what happens when one defocuses? You know, when one focuses, all the rays, I guess, that come into the lens are projected onto one spot.
Yes. So
that is also the plane of the eye or the plane of the film or the sensor.
That's correct. So if you have a good eye or a good camera or a good telescope, the light should all come to a nice sharp spot. And in fact, there's a lot of work that goes into designing telescopes and camera lenses so that, you know, when you take an image of something, all the light goes into a nice tiny little spot. And so in the case of this telescope, the reason the image of Sirius looks the way that it does is there's this big mirror that's light's bouncing off this larger mirror, and it goes to the smaller mirror, and it's in the way of the light that's coming in. And so it's basically blocking all of the light that's coming from the star. And when you are in focus, you don't notice it because all of the rays are coming into a nice focus. But when you just go out of focus, as shown in the middle picture over there on the screen, you start noticing the shadow of it's what's called a secondary mirror, which is in the center of the telescope. And so that's why you get this big annulus in that image.
And so what this image, this drawing shows is kind of a schematic representation of all the different light beams that hit the sensor.
Exactly, yeah. So
and each one of these dots bounces around in its own way.
Exactly, yeah. So each one of these dots that you see, it's going through the telescope and eventually ending up on the sensor. And this is actually created by a program that we use to design camera lenses, etc., where you send a gazillion number of paths of light or rays of light through the optical system or telescope, whatever it might be, and then see where they land on the sensor plane. And that's how we design optics.
Because I think, Kyros, you then threw in the word interference, which kind of really, became so, made it really clear what is happening. Can you explain
a little bit, yes.
A pool in sunlight with...
Right. So the thing about light is that you can think of light in many different ways, and one of them is almost like a wave. So
maybe a little closer.
Yes. So imagine, for example, that think of a drop of water falling into a pond which is still. What will happen is it'll create a wave, and you'll see that wave expanding. And you can think of light coming from the star as a drop of water like that. Now, if it's only one drop, it's fine. But if you have many of them, then and they land at slightly different places on your camera's sensor or the film, what ends up happening is that you have these two waves which are, let's say, expanding separately, and then in some places they add up, in other places they cancel out, and you get this very strange pattern that you see on the right over there. And that also is a physical effect that you just cannot avoid. So you have this combination of what's called interference of light, as well as the chromatic effects that are due to the atmosphere itself. And so that creates an even more complex appearance for what you end up seeing.
Which looks as if there is something, and actually for this split second, this was there. So this is not after effects, this is not something bad happening in the telescope. This literally was what was there in front of the telescope. This is nature.
Right. That's correct. In fact, I did see your Instagram post, and that got me thinking about it. And one of the things that helped me figure out what it could be is that it's happening very quickly. If you noticed when you walked in here, you were watching the video, and things are changing. The colors are changing very quickly. The shapes are changing very quickly, and that's not possible to do within an optical system. And that was the clue that I had, that it had to be the atmosphere, because the atmosphere actually changes very quickly. In hundredths of a second, it can change. And so that's the fact that it's changing so rapidly was the clue that led me to think that it's just the atmosphere.
What heights do these changes take place? From 0 to 10 kilometers, or where is the turbulence?
Oh, that's a great question, and it depends on where you are. And so if you're if we're just outside, I was just talking to Kyros before we started this conversation that I have an 8-inch myself, and I don't have a good spot for it at home. So I put it out on my driveway, which is this black asphalt thing, and usually I observe in early to late evening, and black asphalt heats up in the day, and then in the night when it's cooler above, it's actually creating convection currents, and that ruins all the images that I take. So I've been thinking about getting a little buggy that I can take my telescope to the park nearby.
And so that I see a little face up there that is not science. And maybe just to get to not too deep into this question, which I will never understand, but the Kyros, could you illuminate for 1 second this, what is it, an absurdity or a contradiction that physicists just quite easily talk about light as both a wave and a particle? How is this possible?
Oh, that's a very, very difficult question to answer, and I'm not a physicist, so I cannot really give you a clear answer here. But we can observe both effects of light when we take pictures, it turns out. So we have sensors today that are sensitive to individual, what's called a photon, which is this particle of light. And you can think of light just like a wave or like a straight line as propagating as you saw before in these figures. But you can also think of it as little bullets, that basically just move individually and bounce off of surfaces, and they end up hitting a pixel on our camera sensor, and that we can detect, and we can detect them as they come one by one. So we kind of get this. We can actually see these photos formed by these photons coming in one by one and hitting our sensor. And we'll get to that, I guess, a bit later too as well.
So that it is a particle is literally proven by
Yes.
it being events that arrive.
Absolutely.
So it's not a continuous ray.
No. And so
And is a radio wave then also particles arriving in bits and bobs?
So Suresh is a better person to answer that, but I would say from the physics perspective, it is. It's just that they arrive much, much closer to each other. So when we talk about, let's say, light is very bright, it just means that these particles are coming in fast. If the light is dim, they're coming much, much slower. And when I say slower, it could be fractions of a second, or fractions of a tenth of a second, or maybe a hundredth of a second. But when the light is bright, you could have millions of them come within a second. So in radio waves, I think the rates are much higher.
More. Yes, yeah, and that's correct. But it also depends on. I don't think there's a clear answer one way or another how to think of this, but I do think of it in context on how we detect light. So in the radio waves, it turns out the easiest way to detect light is as if it were acting like a wave. And we have antennae that are designed to detect waves of light in its wave form. And it's optimal to do that in the radio, but in where our eyes can see, the best way to detect light is in its particle form as photons. But if we were to do that experiment that Kyros had shown, that diagram, the interference pattern, and we put a camera behind it that can detect individual photons, initially we'll see the individual photons arrive, but then over time, as the signal builds up, you'll actually see the interference pattern. And that's pretty mind-blowing. That suggests that the light, as it travels as a photon, if you want to think about it, knows that it has to interfere with itself.
I leave you with that. Just you can see this yourself from roughly, I guess, next month. Sirius will be first visible in the later evening hours in the southeastern sky, and then throughout the midwinter it dominates the southern sky and disappears roughly towards end of March. You can be guaranteed that you can tell it's Sirius. It's quite sort of lowish, and it's the brightest star you can see, and it twinkles like hell. Because anything brighter, which at the moment is Jupiter, I guess,
Saturn's coming,
and Saturn, but they have a calm light, but this Sirius, which is really visible from pretty much anywhere on the planet, on the southern hemisphere as well as the northern hemisphere.
I think so, but I'm not 100% certain.
And it's a beautiful spectacle. Coming to maybe just put in focus this instrument that we all have, or those who are lucky enough to have it, the eye, which I once did a similar session with an optics professor from Imperial College in London, and he broke news to me that the the image that the lens of the human eye projects onto the retina is actually of terrible quality. And that a whole lot of post-production is done in the brain. And we maybe talk a bit more about these specifics of the human eye, but one particular is, of course, that the world that we see is a spherical world. Is that the right term? Is it spherical? Yes. And the eye is a sphere, and so the eye doesn't have to compensate for any translation for flattening the image, but a camera has flat film. You print on flat paper. The sensor is flat, and so as we started corresponding, Kyros and I, he was mentioning the term computational photography, which is the world we're in now. No? What is happening in your iPhone or other smartphone is no longer referred to as digital photography, but it is computational photography, which Kyros can maybe go into. But I wondered, like, how is it possible that with all this incredible power, they are still not able to avoid my friend Vasil's head to look completely distorted on the left corner?
Right. So part of the issue is actually how we perceive the world around us. So, when I look at you or I look at the auditorium in general, what's happening is that my eye is actually moving around, and as it moves, the pupil of the eye is changing, to be able to see something very bright or something a lot dimmer, and at the same time, it's our brain that actually creates this image that's formed in our head, because the high resolution, let's say, part of our vision is about what I can see with my thumb when it's about a meter away. So that's the only high resolution part. If I aim my eye at a particular point, that's all I get from my high resolution part of my retina. So the reason we're seeing the world in a lot of detail is because our eyes are moving around. And if you think of living in a bubble, looking around you, then you can think of it as being spherical. You're kind of in the middle of a sphere, and you're looking around, and that's kind of how the image of your is formed, of the environment, in your brain. But when we print a photo, when we capture a photo, it's flat, and so being able to basically show this spherical world on a flat piece of paper is not that easy, and so. That basically is what creates these distortions, is because we are trying to kind of show a sphere on something that's flat, okay? And no matter how much we try to fix it, there's gonna be some distortion, no matter what it is. If we wanted to show it on a screen, the screen is flat. We're trying to show something that's spherical. Some part of that will inevitably have to be distorted, okay?
And that happens the same with the depiction of the continents. And as part of my True Study Center table installation for the last 10 years, I always make sure to include a poster called The True Size of Africa, which really is part of a colonial mindset that is active until today, that we Northerners haven't found it necessary to correct the Earth's map, the world map, to show that Africa is not the size of Greenland, but that Greenland is in fact, I think, 1/10 of the size of Africa. And the Soviet Union, Russia, is not double the size of South America. And that is just exactly the same effect. Is it an effect, or is it a...
It's the result of this projection. So we choose to, project the spherical Earth onto, a flat sheet of paper, and it's up to us to choose which part will be shown small and which part will be shown distorted. Mm-hmm. And it's the same thing with photos. We want to show, let's say, the center of the photo as being, normal appearing, but then when you want to show something that has a wider field, like a photo that has a wider field of view, the rest of that photo will be a lot more distorted. So here, for example, you see the lines, even though, for example, that, I don't know, it's a bridge, I guess, even though it's straight, you end up seeing it kind of distorted like that.
And the only way to kind of straighten it out is to scan it and present it like this.
Well, you're kind of cheating here. So here, instead of trying to capture one photo and display that one photo on a flat sheet of paper, you actually have 3 photos taken by looking at different directions. So you capture a photo from here, you capture a photo from here, you capture a photo from there, and then you stitch them in a way that you can't see the seams, and you get everything to be straight, but you've lost something. You don't have what imaging people call perspective. So this photograph cannot be captured with a camera. It doesn't obey the rules of perspective.
Yeah, it's. I mean, photography's inability to capture and image depth and space always puzzles me. It's an incredible medium. I love it, and I've been using it for 35 years. But last weekend, again, I was shocked sort of how incapable my camera was to capture the layered depth of these magnificent gardens in Southampton on Long Island, which have these prosceniums of different trees, which are absolutely incredible to view with your 2 eyes. And because we can only see 3-dimensionally because we have 2 eyes. And what the brain does is calculate the parallax between one and the other eye to understand depth, and you can just here see this parallax of sort of the shifting position, and only then you realize that the center of the picture is much further away. I guess there's not much to say about it because, I mean, I asked you earlier, there is no real new 3D photography coming, no? Because the red and green light glasses from the 1980s or so, that isn't exactly satisfying, but then also the polarizing and IMAX images somehow lock us in this particular viewing experience. So you don't think there will be something coming which you can just look at freely and get a 3D hit from?
Well, there's virtual reality goggles, and if you wore that, and obviously it's not as comfortable as looking at a screen or looking at something, but they can create the perspective. If you can take an image with the 2 different perspectives that's comparable to how our eyes see things and how our brain stitches together depth of field, you could project those 2 images and get a sense of depth from that.
Mm-hmm. I would say, well, in fact, there are ways to capture the world in 3D, but I think before we get to that, one question is, who do we want to do that? Do we want our brain to do the 3D perception, or do we want to have a computer do it and then show it to us? So these are 2 different things. For example, if I were to take the 2 photos that you showed me, that you showed here, Wolfgang, and you just show one of them to one eye and the other one to the other, you will see you will perceive that as being 3D. That's done by your brain. It's not done by the computer. And there are efforts, although I wouldn't say anything conclusive yet, about displays, computer displays, like your screen, your computer screen, that will actually do show 2 different images to the 2 eyes without the need for the kinds of polarizing glasses and things like that we have so far. The problem is resolution. So, the displays that you have now, the computer displays, they have many, many megapixels, and we don't really have displays that show 3D in that level of detail today. But whether it will happen or not, potentially. That said, there are cameras today that allow you to capture 3D photos. So instead of, for a pixel, all you have is, let's say, red, green, blue colors, which is what a typical photo has, you can actually also get a distance, how far away from the camera it was. That is still very much in development, but even your phones have it. A rudimentary form of that, but Face ID and a whole bunch of other sensors developed by different smartphone manufacturers. They do actually have these kinds of sensors.
Sorry, so the Face ID is really measuring the different running times of the speed of light from the cavity of your eye socket to your tip of your nose. Is that how they recognize that this is not a 2D picture that it is shown?
I mean, the phone itself, it has a light source on it. It's like a flash. Think of it as a flash. It sends off a bright flash, and then it counts how long it takes for that flash to go to your face and come back. Okay? And that time is related to the distance, because light actually is finite. It has a finite speed. We were talking about this before. In astronomy, we talk about light years, right? How what is the distance that light has to travel for it to take a year to get there? And we're talking about 300 kilometers a second. But there's the flip side of that, which is small distances. So light, in order to travel, let's say, a distance of about 30 centimeters, takes a billionth of a second. If you think that's too short, it's actually not that bad. If you think about your computer, okay, the CPUs, the computers that you're using today, they can execute billions of instructions per second. So that means that one instruction is a fraction of a billionth. So it's not inconceivable to think about computers or cameras that can actually measure these kinds of distances, which are called time of flight. And we're there today. We do have sensors that have this capability.
Time of flight. Beautiful.
Yep.
I mean, I love the language of science also. So is it really that the flash is obviously not send invisible light because we don't see it, but does it then measure the distance, the different traveling times of the relief of our face? Or how does it authenticate that we are who we are and not a photo of?
Okay, that is kind of a different story. The question of how do we take that distance information and convert that into an authenticator. But in terms of what actually happens is, yes, there is let's say a photon is emitted by the camera, by the light, this little flash. It travels, it bounces off a particular spot on your face, and it lands at a particular pixel. And in that pixel, there is a little device that can measure this time and convert it to a distance. So what you would get in the end is something almost like a color photo, except that instead of just having RGB, red, green, blue, it also has depth.
Oh. Staying closer to, well, I don't know what the bridge is here, but the visible, the aesthetics. We are in an art museum, and I started to reach out to astronomical observatories if I could come and visit. And the good thing is, these are usually all taxpayer money financed, and
right.
And therefore they have a public information duty almost, or interest to present
Both.
their work.
Both, yeah.
Duty and interest, and so they are obviously not open walk-in places, but I was lucky to visit two of them. One of the largest telescopes on Earth, the VLT, the Very Large Telescope, very imaginative name.
Just like time of flight.
In Paranal, in the desert, Atacama Desert in Chile, and here in the European Northern Observatory, the Swedish Solar Telescope on the La Palma island of the Canary Islands. And in both cases, I was struck just how, I don't know, I don't want to offend, but...
No, you can't, don't worry.
Banal and mundane and unexciting these workspaces look like. and I realized, like these astronomers, they look at these cheap Acer screens and some gray. Usually, in the case of Chile, it was all amber lights, or in the case of the solar telescope, there was also this strange screen which was constantly moving. And I think this has something to do with Suresh's main area of work, adaptive optics.
Yes, that's true. Well, we have Acer screens because we're funding limited, so got to use the money for all the instruments that cost a lot of money. So anyway, yes. So adaptive optics is actually a way of trying to remove the blurring from the Earth's atmosphere. If you remember looking at that image of Sirius, you would be able to basically get rid of the motion of the star and all the twinkling that you see. It's pretty complex technology. And this image here is, I believe, looking at the sun with something that looks like the eyeball of a dragonfly. So lots of little lenses on it, and each lens goes to a given square over there that you see. And it's all looking at the same patch of the sun. And so you kind of see they're all look roughly similar. And
is that a sunspot that they are focusing on, or what is this black?
It looks like a sunspot. I can't say for certain, I wasn't there, but it certainly looks to me like a sunspot. And what you're doing is you're taking pictures of all of these, and each one of this lens is going through a different part of the telescope. So it's looking through a different part of the telescope, just like when we were looking at the image of Sirius. And so it's looking at light that's coming from the sun at a given location and going through a different part of the telescope, which means it's going through a different part of the atmosphere. And by looking at all the images and how they differ from each other, you can figure out how the atmosphere is actually distorting the underlying image of the sun. And you can try and fix that.
And now I think a penny drops with me. Is it, so this is done computationally? This is not done by moving the mirror minusculely? Because I thought that adaptive optics is that they measure the movement, and then at the same time in a millisecond move the mirror with a little device and flex it and bring it all together, or is it just stacking all 50 images on top of each other?
No, this is not the actual science instrument. This is just the measurement part. And then there's a special mirror in the telescope that is really thin and has little, basically poke this mirror into any shape. So it has lots of little pokers or actuators. And from the measurement, you can figure out how to shape that mirror such that you subtract out what the atmosphere is doing. And
so it's in constant actual movement.
Yes, it's constantly moving. And the measurement part is the computational part, and then there's the physical part where you apply. And
at an 8-meter telescope in Chile, they also move the 8-meter mirror?
No, you don't. So this thing needs to move very fast. It needs to move every thousandth of a second. So a big 8-meter mirror has too much inertia. You can't move it. And normally the scale of the atmosphere is pretty small, and you need to have about whatever the number is there. Each image will correspond to a position on the mirror that you would change. So 100 spots on this mirror you have to change at a thousandth of a second. And so it's impossible to do on a big mirror. And what they do is they shine the light from the big telescope onto a smaller mirror, which is very thin. It's probably a few inches, an inch to a couple inches in size, with the actuators on it. And they fix the light that's aberrated by the atmosphere, and then send it to a camera or whatever it is that's looking at the night sky through the telescope.
Is that the secondary mirror, or is that a third one only for the adaptive optics?
That's a great question. Usually it's a third or fourth mirror somewhere in the system, but now the secondary mirror can also be used to do that. Technology has been improving.
And we're moving to the sensor.
Before we do that, a couple of points. First of all, Suresh is too modest, and I wanted to kind of object to what you said about their workspaces being boring, because there are actually two types of astronomers. There are at least that's what Suresh told me when I first met him, I don't know, 6 or 7 years ago. So there is one set, which is people like what you see here on these photos that are kind of watching at the screens, right? And maybe interpreting the data that these screens are showing. But then there is another tiny set of astronomers who actually work on creating the instruments that are going to these telescopes. And that's what actually Suresh does. And if you go to his lab, it actually looks like, you know, a set from a science fiction movie. So it's actually not looking at screens. It's actually looking, you know, designing the sort of innards of these telescopes, which is, you know, much more extremely sophisticated work, mainly optics, that does that. And maybe I should mention there's actually one thing that Suresh and I have been working on over the last, I don't know, 5 or 6 years, which is that, you know, it relates to one of the things that he said, that you measure the atmosphere and then you have to correct the mirror in order to kind of undo the distortions of the atmosphere. But the problem is, by the time you measure it, it's changed. So what correction do you put? Okay, so you have to predict, based on your measurements, you want to predict the correction that happens next. And that's where AI comes in, and we have actually a student who's working with us on that particular problem.
Thanks, Kyros. And if you have some time, you can always come and visit me in my lab and see how it looks like.
I will take you up on it. On that night in Chile, on the mountain, that I was allowed to spend with the astronomers, far away from the telescope, by the way. I was allowed to go to the telescope at 6 for sunset, because after that, they open up the dome. And if a human being is in this 30-meter huge dome, only that presence of that body's warmth gives turbulence that disturbs the viewing conditions in the desert. So we were in this not so exciting office space, and I was looking at what they were looking at, and I was asking, "What is this?" And they said, "That's an unnamed galaxy." And then I pointed at that. They said, "That's a dead pixel." So I just found this so incredible, no? That the smallest unit can be like an electron, a pixel that doesn't know is there information or no, or it's a little bit blurry and it's an unnamed galaxy. No? So like this bigger one, they could say, yeah, that has a name, no? But this other stuff, they don't even name. No? And then that was fascinating to me. These sensors are working, I mean, astronomy in general is working pretty much always in the area on the limit of visibility, of what can be detected and is there something or is there not something? And so the sensors are, I guess, cooked to the limit, to push to the limit, where they become extremely noisy. And what is real signal, what is no signal? And so each of these sensors, which are here, you see one of them, and this telescope has 16, which you see on the top left there, image there. And each of these physical little things has different electronic charges and makes different false images, or actually has dust on them. I think you can literally see there's physically some dust on them. And so they run through 16 of these sensors and then stack the 16 images on top of each other. And obviously, only what is in all 16 of them is real information, and the rest is discarded.
That's right.
Correct?
That looks like infrared. It's an infrared sensor, I think. It looks at light in the infrared, if I were to guess. They tend to be, you get very good infrared performance, but they're hard to make. And so they often come with a bunch of bad pixels, dead pixels, and you just accept it as it is. And what we do is, one way to do it is to take multiple images with different sensors, and then first of all, you need to know where all the bad pixels are, so you ignore the data from there, and then you basically stitch the images together so you get a nice clean image out of it. And you're absolutely correct that we're always pushing limits on technology and methods, and we basically need to detect every little bit of light coming from these, distant objects, and for that we really have to push the technology to the limit. And one thing I do want to mention is even our camera sensors, they're not, in our cell phones and on our DSLRs, they're not perfect. They will have dead pixels in them, but we don't know about them because the manufacturer actually catches them, and then the computational side of things takes care of it, fills in the gaps. And so you get really nice, clean pictures, but there are hot pixels and dead pixels in our cameras too.
As far as I understand, the majority of high-quality sensors are made by for consumer and professional cameras are made by Sony, and maybe another few makers, which is where I want to go in a sec. But I wonder who makes. So if only like a few companies are capable of doing these high-end pixels, who makes these even higher-end ones needed for astronomy?
So that's a great question. I think the consumer products are getting to a point where they're really, really good, and astronomers are starting to look at, Sony sensors, etc., for doing astronomy. There are other companies. There's companies that do just scientific sensors, image sensors. There's a British company called E2V, and they've been purchased by this large conglomerate called Teledyne Imaging. And now that company has basically a monopoly on a lot of scientific imaging sensors.
In 2014, I was in Tokyo and able to meet a group of Sony camera developers, which was exciting to realize that they actually looked at my work and they thought of a camera looking at my work, and then meeting me. It was an incredible encounter, and because obviously these companies are very secretive, and I asked them, how is it possible that in recent years the light sensitivity of my cameras have doubled and quadrupled from, it was incredible that you could shoot at 3,200 ISO, and then a year later it's 12,000, and then 3 years later it's 25,600 ISO, and allowing me to make from 2010 onwards, when I started to go fully digital, to make pictures that I would not have otherwise, could not have taken before, like this picture called Munawata Sky, which is upstairs on the 5th floor. To make an astronomical picture showing that amount of stars without the stars moving or without the island moving in the sea would not have been possible. But this had an exposure time of only 3 seconds, which is so short that you don't see the movement of the Earth. And the technicians then said, no, hardware doesn't change. There isn't like a different silicon in the chip, but it's only the computing power that counts out the noise. Is that really where all this advance comes from? It's mathematical.
It's both. On the device side, you can consider the following. Okay, so let's say astronomers, want a new telescope or need to invest in the sensors that go into that telescope. There is a certain budget for that, and these are expensive sensors to make, one-of-a-kind sensor, right? Okay, let's go to the smartphones. You have about 3 billion cameras manufactured per year. So investing...
Sorry, wow.
Yeah. So investing, having a company invest billions, far more, many more billions in the technological development of those sensors is going to be a lot more, profitable and will have a much bigger impact. So that's one of the reasons that, in fact, the camera sensors today in our smartphones are really pushing the technological limits to the extreme, in a different way perhaps than what astronomers need, but for sure they are at the cutting edge of technology.
It's minerals, or what do they put in there? Is it processes or is it materials?
Maybe I'll take a bit of that. So one of the things that Sony did recently, which has really improved the quality of these sensors, is the sensors collect light, and you have to get the light out. So the way they collect light is they turn light into something they can measure, which is electrons. And then you have to pull that out and then, do your measurement, and then you get your image. And so previous sensors had wires that ran in front of the sensor itself. So the light would come in, some of that light would get scattered by the wires, and then it'll get into the silicon and then generate the electron. So they weren't as sensitive. So for every photon of light arriving, maybe 50% of the time you'll get something. So Sony came up with this cool technology where they can flip the whole thing upside down, where the light would go straight into the silicon, and then all the reading out of the electrons would be on the other side where it couldn't impede the light collection. So that's what's called a back illuminated sensor. And they found a way to mass produce that, and that in itself probably gave a 50% improvement in light collection. And then the other technical side of things is the actual measurement, turning those electrons into some signal that then can go into the computational engine, which is going to further improve the image. So there's been a lot of innovation in that in the measurement electronics, so that you can get lower and lower noise pushed to higher and higher ISO. And so those have been two major technical developments. And of course, then there's the computational side that gives you even more gains.
Yeah, for example, there was, there is, let's say, Apple, which I think has been using like the top line sensors for a very long time now, by Sony, I think. And Google came up with its phones a few years ago, and they didn't use the highest, the top of the range sensors for those phones, but they put a lot more computation behind them, and that ended up getting to the point where these the cameras, which means both the sensor and the algorithms that came after it, actually were competing or even higher performance than from other companies. So algorithms are becoming much more important, not only in terms of functionality, like what you can do with your camera, what kind of pictures you can take, but also in the core quality of the images you get.
And profitability, because the algorithm is ultimately cheaper than buying the top of the line sensor.
That is a business decision as to how you want to go, right? So of course you want both if you can and do it cheaply, but yeah.
So I've been using this, also this cooking the sensor to its limit in these photographs and of the night sky, and in particular a type of picture that I would not have even dreamed about possible until 2010, which is called In-Flight Astro. This is taken from a flying plane across the Atlantic at nighttime, and it shows Cassiopeia, the constellation. I pushed, I guess, the brightness as much as the computer allowed me, and it brought all that noise to the fore. And so there is also the limit of like what is an actual star and what is a pixel that doesn't know if it carries charge or it doesn't. Is that how one could describe noise? A pixel not quite knowing? Is there something or is there nothing?
Yeah, that's one that could be a way of looking at it. Yeah, you can't. It could get noisy to a point. I think there's a nice photograph of the moon and yet the earth shine. Maybe you're going to show it in a second, where it looks very grainy, and it's hard. You know, if it was an image of just a blank sky of the night sky, it would be hard to tell the difference between the star and just sensor noise. But a lot of times you have a little bit more information. The star is probably not just one pixel. It covers a few pixels, and then you can use that as information to distinguish between noise and real stars.
This one I made in 2020 is called Crossing the International Dateline. Where do these colors come from? Because they are certainly not in the sky. Do you have any clue?
It's all, let's say, we call them artifacts of the sensor. So they are, pixels individually, they don't record all three colors. They record red, they record green or blue. They don't record all three. In fact, all the pixel really does in a sensor is record brightness. And what we have is filters, little color filters in front of every pixel.
Is that a physical little?
It's a physical filter,
really?
yes. It's kind of after you fabricate the sensor, you kind of send it to another, let's say, somebody that basically takes that and kind of adds a filter on top.
Really?
Yes.
So 8 million, or like my camera has 20 or 25 megapixels. So there's 25 million little color filters in front of each.
Correct. Yep. Yeah. So in reality, if you have, let's say, 20 megapixel camera, like a sensor, then 5 of those megapixels are actually, so if it's 20, then 10 of them are green. 10 million would be green. 5 would be red. 5 would be blue. Now, you may wonder why, right? Because our eyes are more sensitive to green, so you want to get that with more detail, right? You want to be more accurate. But what that also means is that if you actually look at a little piece of that sensor, you have 4 pixels, let's say a group of 4 pixels. 2 of them are green, 1 of them is blue, 1 of them is red. And then how do you create a color photo out of that? You have to kind of fill in the missing details. So where you have green, you need to figure out what should the red be there and what should the blue be there. Because you don't know it. You didn't measure it. So that's done computationally. And so when you have noise in these pixels, which happens when you are really pushing the limits, then that noise is in these pixels, and then that somehow gets converted into the kinds of images that you see, which have these color rainbows and all sorts of other effects, potentially.
This is the Northern Lights photograph close to a summer solstice, so the sunrise on a flight from New York to Berlin was fairly up high north, and so the dawn and the northern light were appearing in the same frame, which I'm quite pleased about. But I must say, like the aesthetics of Northern Lights photographed are so overwhelmingly the same that it is almost impossible to make them really your own, I found in my experience.
Well, that one's a pretty unique picture.
You think this?
Yeah, I think so. with the sunrise coming up, that's definitely unique.
Okay. I mean, I thought so too. I thought it's wow, like you were in. I was in night a few minutes ago, and suddenly there's like this first faint beginning of a day, and that they coexist. But I guess we are. How are we doing for time? But let's look. This is the photograph you mentioned. No, the like the exact pattern of what you see in this noise. I guess we would call it random, no? But there is a decision that led to each pixel acting the way it acts.
Yeah, and it's random. I mean, here probably this is the sensor kind of acting up. The individual pixels, they're receiving very little signal, and we are kind of trying to. It's very dim. You're trying to amplify that somehow to make it visible, and that causes these effects. I don't know if Suresh has any
I think
thoughts.
that's what it looks like. It's got a salt and pepper pattern to it, which probably means each pixel is just randomly flipping back and forth because there's not enough light.
Yeah.
But I should say that we are maybe a few years away from maybe developments that will allow us to get much cleaner pictures, because again, the pixels will be sensitive to individual photons, and if a photon doesn't arrive, it will not give you a random value, it'll give you a 0. So those are sensors that have effectively 0 noise. If you know.
And is that a physical, again, is this minerals? Because I'm always fascinated, what is this stuff? And are we there also in this raw earths and stolen from mines in Congo? And
it's not different than the sensors we have today in terms, technologically. They are using kind of the same, it's called CMOS technology, the same kind of technology used to create your chips for your CPUs and everything else. But it's kind of new ways of thinking about a pixel. So rather than having that pixel kind of spit out a number, which is how much light it received, this is happening today, this pixel would spit out a 1 if it got a photon and a 0 if it didn't. And there's nothing else. If there's no photon, it'll give you a 0. It won't give you a random number. And then you just count them.
Just quickly for the record, what are sensors made of? Is it silicon or is yes? And yes. Silicon is a kind of sand or glass, or what is?
Well, it's made from sand. It's an element, so you purify it. You start with some special sand, and you can form a pure silicon crystal, which has almost no impurities, and that's where you start, and then you make your computer processors, you make your camera sensors, what have you. It all starts from that.
Okay. This is a photograph I took of the partial solar eclipse last year in Berlin, and I thought it was interesting to place the moon in the center of the image, and it was very cloudy, so this was photographed without a sun filter.
Okay.
A little bit dangerous. Have the whole telescope.
As long as you're not looking through the eyepiece.
Yes. But so this is photographed at a higher speed, and the cloud is shown in this great detail, making it almost look like it is a little bit like the sphere of the moon. But when one looks closer, do we have the close-up? Yeah. I was wondering, is this actually the profile of the lunar landscape, the valleys and mountains?
Yes,
or is this turbulence?
Actually, the way I would look at it is, if you look at the sun, that looks perfectly sharp on the edge, so you don't see any features there. And if it's turbulence on the moon, you would see the same types of features on the sun, but you don't see it in the sun, but you see it on the moon. So it's very much the surface of the moon and the ridges on the surface. Yes. You can actually see that, which is pretty impressive.
So seen from the moon, a solar eclipse with a Himalaya on the side would look quite jagged.
Yes.
This is a quick view into the current exhibition at David Zwirner in New York called Fold Me that opened this week. Yes. And on the left is an aerial view of Abidjan and Ivory Coast at night, and in the center, a 3 by 4 meter sized print image called Lunar Landscape, but it's actually a seascape lit with white moonlight, but the moonlight is white because it is only reflected sunlight, and water doesn't have a color, so the ingredients here, the picture is completely black and white, whilst it actually is a color photograph, no? Made with a color sensitive camera. And which brings me, like anyone who has seen obviously like a full moon night sees how bright the landscape can be, and I've always been fascinated since childhood. This photograph I took in 1980 when I was 12. Is by a phenomenon called moon in earth light, more familiarly actually called moon in earth shine.
Yes.
Earth shine, which is due to the reciprocity of the phases of moon and earth. So when we see a full moon, somebody on the moon would see a new earth, and vice versa. And so what a person on the moon would see in this night, in the dark bit here of the moon, they would see an Earth that is 2/3 full. And since the Earth is 3 and more times larger in surface than the moon, they have a pretty big Earth in the sky. And if that is almost fully lit, it makes a really bright, full Earth night. And that is the shine that you see. And what I always found so romantic is that this light is actually the Earth's light, and I'm part of that light that is reflected to the moon and coming back.
Right, and in fact, you should be able to see it with your eye, especially in this phase of the moon, the part of the moon that's lit up by the Earth.
Which is available for everyone to see in the second, third, fourth, maybe fifth day after new moon, or before new moon.
So tonight.
Is it?
I think it might be the second day after new moon, or third day.
Because when we were installing in March, we could definitely see it. But of course, the moon is very low after sunset. But it's fascinating to see. You see the thin crescent, but then you see the whole disk of the moon, and that is actually light reflected from Earth back. So, I mean, this one was a little bit of a mystery. I hope that Kyros could shed light on it. It's also moonlight reflected on the Mediterranean sometime 2011, and I was puzzled why are there some reflections that have a magenta shine and others that have a green shine?
So I just saw this photo a little while ago and got this question. I'm not entirely sure, but one thing that does happen is, depending on so in a photo like this, you have light from the moon hitting the surface of the water and then coming to the camera. And for light that is for reflections that are very close to the camera,
a bit closer.
For light that is that is reflected close to the camera, the angle at which the reflection happens is different than if you were looking at a distant point and then light from far away sort of traveling to the camera. So the angles of reflection are different. And when the angle of reflection is different, there is kind of a basic physical property of light that different wavelengths are going to be reflected in different ways. And so you end up potentially getting an effect which has to do with just the angle of reflection is different.
Just to make the they are not diptychs, the two, but they sit next to each other on the wall in the gallery in New York, because I take great pleasure in the color of light and how it is translated by film or now sensors. In New York at the we have it up here as well. In New York at MoMA, there was a big print. Here at AGO, there is a medium-size 50 by 60 centimeter print of a work called "The Color of Money," which was still photographed with film, with a 1600 ISO film in 2003, landing in London, Heathrow. You fly over the city of London, and the bank towers at that time were all still lit by green fluorescent light. And so there's this cluster of green light surrounded by the yellow sodium light. And here now, 20 years on and a different continent, you still have the sodium lights for the big streets in this African capital, but African cities at night are much, much less lit, and wherever you see here a blue dot is a recently installed LED light, and so I find it fascinating how the surface of the world one can read. You know, it's not just superficial. There is always a reason for how things are and look.
That's right. And obviously, there's been a big move. Sodium lights are very energy efficient, but they have this very yellow color to them, and they've been around for a long time. But now the LED lights are comparable, if not better, in efficiency. And there's a strong move towards that. In fact, all the street lights are being replaced by LED lights instead of the old sodium lights.
And I mean, it feels like, at least to people in my generation, that we've cycled through different light sources quite quickly with banning the traditional incandescent light bulb, but then bringing in the really unsatisfactory energy efficiency lamp, which fortunately, I stored up on incandescent light bulbs. But by the time I could get to the end and got never near the end of the stash, when it became clear that we don't have to live with the energy efficiency bulb forever, but instead that LEDs were able to produce white light and different colors of light. Do you think that we are now for good with this light source? Or
I don't think we can make a wager on that, but I think LED light sources have really, there's been a lot of innovation that's happened over the last decade. You know, the color and quality of light and longevity, they just win in many different ways compared to existing light sources, and of course energy efficiency. So you get all of that plus energy efficiency. So I don't know what's coming next, but at least they're here for now.
Any predictions from you?
No, I don't have any predictions, but I should say one other thing. It's not just the color, it's also the flicker. So sodium lights, they flicker a lot. Incandescent lights, they flicker a little bit less. Fluorescent lights flicker a huge amount. The early LEDs also flickered a lot. So you went into a room, you kind of couldn't figure out why you just don't feel well. and it's because of this flicker, very, very, flicker that's happening too fast for your eyes to notice. If you have a fast camera, you can actually, or a smartphone, you can actually notice it. And in fact, there are all sorts of algorithms down there in the camera to kind of undo the flicker that exists. But the LEDs are now getting good enough that you don't really have that kind of flicker anymore. And so the quality of the light is actually a lot better, in addition to the color, of course.
Actually, going back to the eyeball again, our peripheral vision actually is much more has much higher frame rate, so to speak. So we can see things that are moving off from the shadows. And in fact, that's usually where you get when you walk into a room with flickering lights. It's really that part of our vision that's picking up on the flicker, and it makes you feel unsettled.
Special art art viewers' experience is going into video rooms and quickly turning your head, and you suddenly see a rainbow. That is that flicker also. And so, yeah, light is of fascination to me from many aspects. And for example, in the later 2000s, early 2010s, I observed how car headlights became ever more aggressive in their outlook. And there's really no reason, no? It's only a projection of the manufacturers of their customers' wishes, how to project themselves on the street, which is a pretty dark reading. But car design has fascinated me always, because it takes 5 years or more to bring a car to production level, and so the makers have to predict somehow what they think the future will be. I carried this observation with me for years, only to on a travel to Tasmania find a underground car park where I was somehow left alone, and it was great bright fluorescent light where I could finally take those portraits of these menacing eyes.
One thing I did want to mention is car headlights have moved in technology too, in terms of how they generate the light. Before they were incandescent light bulbs, and now they use what are called gas discharge lamps.
Not LED.
No, the headlights. The rest of the lights are usually LED, but the headlights themselves use these xenon gas discharge lamps. So they're extremely bright and extremely white light.
I see. And this was part of the presentation with the optics professor, which I sent to Kyros, and you expressed interest. Yeah, like interesting, like a lot of what you show there has to do with this coexistence of scattered light and reflected light.
Right, correct. So, in fact, even in a photo like this, we're looking at the headlights, but in fact, there's no light coming from the headlights, right? It's all coming from, as you say, lamps that were around in the space you were in, and then it kind of gets reflected and bounces around and refracted, and that's what gives the appearance of these headlights now, the way we see them here. There was also this other image. So here's an example of some object that doesn't really have a light on its own. It doesn't have an appearance on its own, right? So if you look at any piece of that, it's like transparent, just like glass. But the shape of it is what creates this interaction, refractions, and so forth, to give the appearance. And what you see here is kind of another object. I don't know if any of you have any idea what this might be. Maybe I'll give you a second to think about it. But it's actually a candle, right? So what we've done here is use a special camera where we've had that camera kind of block away all the light that happens inside, that bounces around inside, and what you see on the bottom is just the reflections from the surface. So this is an example of an object where most of its appearance actually comes from the inside. It's not reflected, and that's not just this. I mean, our skin is like that too. Like if I were to take my phone. I'll turn on the flashlight, put my finger there, right? You see all the light coming through, I hope, right? So most of the light actually, even on our skin and many other objects, is actually coming from scattering. It's kind of internal to the surface. And the reflections are actually quite, much less pronounced. But our eyes see everything But we can make cameras that just separate those things out. And that gives us a very different view of the world, actually.
So the internal, like when you say the light comes from inside, it is also light coming from the outside being reflected, but from deeper layers inside the candle or deeper layers inside the finger.
Right, right. So, I mean, I gave
Whereas
you
the one layer that is the actual visible skin is actually not such a huge part.
Right.
It's equally reflected, tenth of a millimeter inside
Right.
and a
And
1
even
millimeter.
more. Yeah, like, I mean, if you peel a little bit of your skin, right, it's just transparent. There's nothing to it. It's really only the interior that actually gives that appearance. Here's another example, like glass, right? So this is just a beer glass. But what reflected on the surface is what you see on the bottom. It's almost no reflection coming from the surface. It's the inside that matters.
PowerPoint speeds us up, but maybe it's also good. This is very speedy because you added this to your mix of things you wanted to. You showed me when we had a Zoom, and this is kind of unbelievable because it shows a bit of light traveling through a Coke bottle.
Right.
And this, can you read frame rate? 500 billion frames per second.
Right. So remember we said that light travels about 30 centimeters in a nanosecond, a billionth of a second. So it's about about the size of this Coke bottle. So that's kind of the video you see here. It's how light traveling in that. And that's a photo it's not like a computer simulation. This is an actual photo. So how was this done? Well, if you were to freeze to a particular frame, that corresponds to it's like taking your camera and instead of having an exposure of 1/100th of a second, you have an exposure of 500 billionth of a second. And you can do that. The pixels can be designed to just capture that light and nothing else. Right? It's just a very short exposure. So you have a flash, and then a few moments later, the pixel gets exposed for that amount of time, and that gives you what you see here. Very precise synchronization between the flash and an extremely short exposure. And then you repeat that, because doing that once is not enough. You don't capture all the light. So you kind of repeat that process millions of times, and that forms that image. And then you do the same thing for, let's say, another instant in time, and that's how you create this video.
So this is basically a still.
That's a still photo.
Made out of the.
Basically, you've frozen light.
Yeah. Easy.
Yeah.
And this is fascinating also. No? This is the same idea of what the skin, what we think this is all reflected from the skin, but it's actually much more deeper.
Right. So this is another example where, the image on the left is basically what you see with your eyes. And your eyes actually get not only the light from the surface, but also the light from the interior. And so all we did here in this particular example is we created a camera that blocks that surface light, so you get to see the interior. It's almost like, you try to look at your smartphone screen out in the sun. You can barely see it, right? It's just too dim. But if you block all of that, you get a much, much better impression. And I think this example here is an amazing example of this particular photo, where all you get to see, right, in that interior part is reflected light. And maybe, Wolfgang, you should say a bit more about how that was done.
But I want to know, how do you block out the surface light? By polarizing, or I don't know how?
That's a bit too complicated.
Okay, we still.
It's optical. It's not a computer algorithm. It's actually what the camera records, but it's a bit too complicated.
Okay, we want to still see the sunset this evening, so we'll not ask you to explain.
Earthshine, Earthshine.
Earthshine.
Yeah.
Oh yeah, Earthshine, exactly. Oh, it's a clear sky. Yes. So please look out
maybe.
after. It's about 6:30 is sunset, so the moon should be visible around 6:50. But what we see here is an example of a group of works, still lifes that I made in my studio starting 2005, called Paper Drop. And the first paper drop I made in 2001, and it really was a sheet of photographic paper, which I taped to a wall like this, and it looked like it was dropping. 4 years later, I observed in the studio a large sheet of photographic paper turned over onto itself, and I recognized, oh my God, this has a drop-like shape. And I photographed it from a particular angle, and it was two-dimensional. The black inside of the paper was two-dimensional, whereas the outside had a depth. Later that year, I started experimenting with it and put a paper on a white table and focused the camera only on the very edge of the paper, which is the depth of field, and the depth was only on that edge, whilst the glossy paper created a tunnel which scattered all the light that came from the wall at the end of the studio where the sun hit, and made this, I guess it's a momentary glimpse of something that makes up what the Sirius pictures could be also, some kind of, it's obviously this is reflections, but why this looks exactly how it does, I also never figured out. But it turned out that it created a almost three-dimensional bulbous effect.
Yeah, I mean, it really is all about how light gets, and it bounces around inside that interior surface created by the folded page. So the reason it appears very dark on the right, in that area, is because light can't really bounce in there very much. So most of the light actually goes into the middle. So it bounces a lot, comes to the camera, but the edges, it's too narrow for the light to kind of bounce in there, and so you kind of get it to be dark. Now, again, this is an amazing example where you've kind of blocked the direct reflection. Like, there are no direct reflections of the page; it's all indirect. If you were to put a smartphone, like the flash of your smartphone, and put it inside the page, you would see a totally white surface. You wouldn't get to see any of this. Mm-hmm. But that's just a distraction. It's still there. It's just that, light, if you were to put a light source in there, you would kind of destroy this effect. It would be much brighter.
Yes, it was great to get your reading of the exhibition, just like these works that I made since 2005, also called Lighter, which turn these temporary paper sculptures that are photographed into actual paper sculptures that are then presented in acrylic glass boxes, and which are an ongoing interplay of the frame and the glossy surface of the paper.
Right. In fact, I mean, when I went through the exhibition, one of the things that struck me was that it's really not just about the photo, right? You have an image, but if you turn off the lights, there's nothing there, right? The only way you can see that image is by light reflecting on it, on that photo, and then coming to your eyes. And so the placement, the materials of the actual photo or the surface that you're showing is hugely important. Your job as a photographer, I suppose, doesn't stop with the capture of the photo, but also with how that photo then reflects all the light from your environment and how it's placed in a larger context rather than just that single image. Mm-hmm. So, we talk about digital photography, but I kind of feel that's a bit of a misnomer, like for today, because everything is analog. Our eyes capture light, it's analog. So there's analog light that kind of enters our sensors, forms the photo, but then we take that photo, we print it, we illuminate it with, our environment lighting, and that's what actually creates our perception. So it's analog to digital to analog. Mm-hmm.
I've always seen myself a still as an analog photographer, because I see exactly that. No, the light hits the sensor, that is an analogous relation, and then I choose not to move the pixels in Photoshop or Lightroom, and so the print is an exact expression of how the light hit the sensor, and that would have been the same with film. Moving to the last chapter of, I guess, solar system geometry. Something I love. When I fly, I always fly sort of with one eye out of the window and the other reading or sleeping. And and when one flies across the line where the sunset happens, one can observe sort of the Earth already having no sunlight, whilst the higher bits of the atmosphere still having sunlight. And this is the first of a small group of pictures where I captured that, called Tag-Nacht, Day-Night, from 2009, and Tag-Nacht 2 from 2011. And so I see like that below that band is literally like the shadow of the Earth cast from the sun. And then this, I believe, and that's my question to Suresh, shows the shadow of the Earth from the sun that is set far over there and is already under the horizon and projecting a shadow into the atmosphere and creating this cone-like.
I think it's probably related to that. One, I guess the mental picture to have in mind is the Earth's atmosphere that can scatter light is probably 30 kilometers above the surface. And so when the sun sets, if you're standing on the surface of the Earth, even though in your perspective the sun is set, if you were standing up high in the atmosphere, the sun is still above the horizon. And so the sunlight will hit the atmosphere there and scatter and create the brighter portions. So the dark side that you see is where the sun is below the horizon, and the rays from the sun aren't reaching that part of the atmosphere. And so in a way, you can think of it as the shadow of the Earth.
But it's the lack of scatter of sunlight, really, in the dark area.
Yeah, the light's not reaching that part of the atmosphere.
Okay. Because a shadow has, of course, the quality that you cannot see a shadow. Otherwise, it wouldn't be a shadow. So what we see here is the absence of scattered sunlight.
That's right, yeah.
This is an eclipse, but what you see is the large disk is the sun, seen through that same telescope in 2004, and the small dot is the planet Venus, which transited across the surface of the sun in the course of 8 hours, just like the disk of the moon transits across the sun in a solar eclipse. And it's an extremely rare phenomenon that only happens every 120 years and then reoccurs 8 years later. And it had very poetic scientific qualities in the 18th century, I believe. Captain Cook, so basically astronomers realized that if we time the entry point of Venus on the disk of the sun from two very far apart spots on Earth, we can then triangulate the distance of the sun. And so there was a mission made in order to capture that time with two clocks, one on a boat by Captain Cook and sent to the South Pacific Sea, and as a result of that trip, Australia was discovered, so to speak.
No, I didn't know that.
And how they actually had clocks that work enough, fast enough, or exact enough, I don't know. Anyway, they did not succeed in the 17th century, but I think in the 18th century they did succeed to measure the timing from two different spots on Earth, and came for the first time to the result that the sun is something like 150 million kilometers from Earth, which was, until then, humans had no idea what scale they existed in.
Right. Yeah, it's pretty mind-blowing.
But what was fascinating was that the observers at the time spoke of a drop effect, that when the sun was about to go to lose, when Venus was about to lose contact with the edge of the sun and move further into the disk, they wanted to time that exact moment. And the observers talk, and then there is a drop. It pulls like a after drop, and only photography proved that this is purely an optical illusion in the human eye. Anyway, I was lucky to see the second one in 2012 as well, which Suresh, you saw as well. No?
Yes, I did. Yeah, I had my own makeshift telescope with my DSLR, but I did put a film in front of it so I don't burn the sensor.
I see. Here in 2004 it was a sunspot minimum, so there is almost no sunspot visible, and then in 8 years later you can see sunspots because they fluctuate.
Yeah, that's a beautiful picture.
They fluctuate in an 11-year cycle, and of course the biggest eclipse, and coming back to where we were in the beginning of the conversation, the biggest and overwhelming astronomical experience I think one can see is a total solar eclipse. And don't go and think we can see 98% from Toronto.
Yeah.
Please make the move to where it is 100%. And in the center of the totality strip, the totality it lasts the longest. So find out where that is. Or if there are better weather conditions in the US, make the trip there.
Well, it might be too late.
Because it's all booked.
Yeah, probably. People are thinking ahead.
And this is 2009 in near Shanghai, and this is 2015 on the Faroe Islands, north of Britain. This was most dramatic. No? There was a hell of a lot of clouds, and we rented a car, Anders and myself, and we started to think, well, the only way we can maybe catch it is by moving and driving somewhere where maybe there is a hole in the sky. And just as totality approached, we found a spot overlooking a bit of sea from an elevated spot, and I put my camera on a tripod and had it on. I mean, these are extremely nervous moments, no? Because it's just like gets darker in this dramatic way, like totality is approaching. Yeah. Where are we?
Times of the essence.
And so I put the camera to a setting of exposure, and fortunately let it on manual and didn't allow it to go on automatic compensation for a drop or increase in light, and so I made this film, which we'll look at now, which is about 3.5 minutes, and it shows the approach of the shadow of the moon and engulfing us in the totality for a couple of minutes, and then it goes away and the light is revealed and daylight starts again. It's silent because there's only like loud crackling wind noises on the audio track. So let's dim the lights. Yeah. I was always curious, are there films like this in science libraries, or have they, because is this dynamic range I guess with film, it wasn't really possible to film.
I'm not sure about that, but I think that's a great depiction of, I haven't seen it myself, but I can imagine of it getting so dark with the eclipse and how quickly it happens. I think everyone seems to focus on the actual eclipse itself, the sun, trying to take videos of the sun, but I think that shows what it's like to be in total eclipse.
Okay, I mean, I learned a lot from you, and you know what? One question I must ask you is, why do astronomical events always get so exaggerated in media? Why every year is there news that tomorrow's moon, the raspberry moon or the harvest moon, will be the biggest in 400 years? Why do we get that? And the reality is that it is an incremental, tiny bit larger than maybe 10 years or 50 years ago. Makes no difference to the viewer. Why does a comet that never even is going to be seen by any person in the street get hyped up to like this huge thing? But like a super fascinating and very simple fact that always makes jaws drop when I tell it to someone. There's a simple reason why a rising moon looks bigger than a moon high up in the sky is because by evolution our brain is trained to see objects at the horizon in a larger magnification. It's purely the brain. The moon is always the same size and only incrementally bigger or smaller for these raspberry moons.
Well, I got to say, I asked the same question when I see the news that, next week it's going to be the next super blood wolf moon, whatever it might be. I'm learning too. I didn't know that you could call the moon many different things. But I think in the end, I agree it's hyped, but it's great that there's interest in the media to talk about astronomical events. And this builds some awareness of the fact that the moon is actually not in a circular orbit around the Earth. It's slightly elliptical, and it can actually change size and change brightness depending on where it is in its position. So I guess that's a politically correct answer. But I do sometimes wonder. And the other thing that you often hear about is Earth 2.0. That's another common thing that's discussed in the media, but at the same time, it's highlighting the fact that we are searching for life outside of Earth, and there are real experiments happening in the world of astrophysics to find Earth 2.0 if it does exist.
Well, I really feel that when we understand the world better, that we will better understand each other. And when we understand common rules that connect us, we will understand that there's less room to ignore or disrespect the other, as we know we are all subjects to the same rules, which might make us more forgiving. And so I have always a feeling that science and teaching science, communicating science is peace work. And so I have always the biggest respect for scientists and those who communicate it. And thank you so much for coming.
Thank you for being here. That's great.
Thank you again to Suresh, to Wolfgang, and to Kyros for your time this afternoon. For I can't help but make the terrible pun of thank you for illuminating so much about how the eyes work, how light works, how sensors work, how cameras work. It certainly forever changes how I think about what I will see in a photograph for forevermore. So, and to amplify, I think what Wolfgang has just expressed. I think thank you for your peace work, all three of you. So thank you again. Please give our speakers a huge round of applause. I will let you know that the gallery is open until 5:30 tonight, so if you haven't already seen To Look Without Fear, the exhibition on our 5th floor, please do make your way up to the 5th floor to take a look. It is on until October 1st. For Nuit Blanche coming up this Saturday, in fact, we will be screening in this very room a film with a first album, musical album that Wolfgang released during the pandemic called Moon in Earthlight, aptly enough. So there are other ways to see the moon if you're not just seeing it out in the sky. Thank you again.